Okay. So last time, sinimulan natin yung discussion sa ng quantum physics, right? Sinabi natin or nagbigay tayo ng mga ilang parameters kung paano natin kung paano yung mga parameters na ginagamit natin to describe variables, to describe yung properties ng mga particles ng mga quantum mechanical particles. Okay, so yung mga parameters na yon ay yung probability density. Okay, so yung probability. Okay, nabanggit din natin yung wave function. Okay, and sinabi rin natin na ang isang property ng probability na to is defined through the normalization condition, which means na yung probability na makita niyo yung isang particle like an electron, a quantum mechanical particle like an electron, is one all over space. And then, sinabi natin or nag-describe din tayo ng mga tinatawag na observables in classical physics. These are position, momentum, energy, time. And in quantum physics, we call these observables. And in order to measure itong mga observables na to, in order to measure yung position, momentum, energy, and time, we use yung concept ng expectation value. So to measure position, we get the expectation value of position. To measure momentum, we get the expectation value of momentum. To get the expectation value of position, so it's a straightforward definition given by this equation na nasa green na box. We also defined an expectation value for the momentum, but we started out defining itong expectation value na to in k-space or in momentum space or yung reciprocal space na tinatawag natin. Eventually, we ended up with an expression for momentum, okay, which is given by this, itong nasa box. Okay, so again, this is the expression for momentum in real space. Pero in momentum space, yung momentum na yan is simply given by this one. So, ito. P, momentum is equal to h bar times yung wave number. Okay, o yung wave vector. Okay, and then towards the end of the lesson, dinescribe natin yung basic equation na ginagamit, fundamental equation na ginagamit sa quantum physics, which is yung Schrödinger equation. We started out with time-dependent Schrödinger equation, and then sinabi natin na we can use the time-independent form of the Schrödinger equation by using this technique called separation of variables, where we separate the spatial wave function with the temporal na wave function. Spatial meaning dependent sa space, and temporal meaning dependent sa time. Okay, and sinabi natin na we can do this if yung potential, okay, nung na ini-introduce natin sa system is not time varying. Okay. So, and then dinescribe din natin yung parang procedure, okay, sort of general procedure kung paano tayo nagsosolve ng problems in quantum physics. First, we have a system, di ba? And we need to know kung ano yung potential ng system na yun. Kasi yun yung ipa-plug in natin dun sa Schrödinger equation mathematically inside the Hamiltonian. Okay, and if this potential is not time varying, then we use separation of variables. Otherwise, hanap tayo ng ibang solution. And then we solve for the wave function, okay, from the time-independent Schrödinger equation. And then to get the time-dependent time-dependent solution, we simply multiply the time-independent solution with this. Okay, again, this only works if V is not a function of time. And then from there, pwede natin i-measure yung position, momentum, and energy. Okay, and then ang binigay natin example towards the end ay yung hydrogen atom na kung saan yung potential niya is proportional to 1 over 1 over r, the inverse of the position. Okay, so we continue with our discussion. Okay, first let's summarize yung mga observables na yun. Okay, so we have these quantum mechanical operators. So so we have a position. So let's see, ito yung description. Okay, kung anong klaseng operator siya. Sa classical theory, kung ano yung operator na yun, and then kung ano yung variable na yun, and then sa quantum theory. Okay, how that variable is defined. So for example, yung position, okay, sa classical theory, we define it as a vector r, and ganun din sa quantum theory. Okay. Momentum, bago muna yan, potential muna. Potential energy, or potential, okay, we define as V of RT, and then ganun din pa sa quantum theory. Not much difference there. Nagkakaroon lang ng difference pagdating sa momentum. Okay, in classical theory, we have this momentum along the x-axis. Pero in quantum physics, in real space, we define momentum in terms of this operator, okay, derivative operator. And then para sa energy, okay, it's simply written as the energy E. Pero sa quantum physics, we have this operator for energy. Okay, so yan yung mga pinag-aralan natin last meeting. Okay, so now we begin with the Schrödinger equation. Okay, so sa classical physics, classical theory, okay, we know na, okay, from 1 to 1, di ba? We know na yung Hamiltonian is given by the sum of the kinetic energy and the potential energy. And ang kinetic energy is nothing but yung momentum squared divided by 2m plus yung potential. So yan yung tawag dito, classical theory. Then sa quantum theory, okay, we have yung Hamiltonian, and in quantum theory, yung Hamiltonian and acts as an operator, and it operates on the wave function psi, okay, which is dependent on x and t if we're talking about one dimension. Okay, and yung p na sa classical ay i-replace natin with yung momentum sa quantum mechanical. Okay, sa quantum physics, quantum theory. Okay, so we write then. Okay, so I negative I. Okay, I remember when you do this, it's p squared is p star p. So we have negative kasi negative 1. Okay. Okay, and then I star, so negative I times I, so that's negative 1. And then h bar squared. Okay, and then may 2m tayo dito, so over 2m. And then yung second derivative, okay, partial with respect to x. Second derivative ng wave function na psi. And then of course you have yung potential, okay, multiplied by the wave function. Okay. In 3 dimensions, so this is in 1D. In 3 dimensions, we have the Hamiltonian operating on the wave function psi, where psi is dependent on position r. Okay, and this can be written as h bar squared over 2m, and then yung operator na del, okay, del squared, psi of rt plus v of rt times psi of R. Okay, kung saan yung del operator, which we're familiar with, okay, operating on the wave function psi is given by this mathematical operation. Then psi. Okay. Okay. So, ang Schrödinger equation natin ngayon, okay, just a bit of trivia. Okay, yung Schrödinger na yan is double O. Okay, and sometimes Schrödinger kasi is Scandinavian. Okay, and sometimes they write it as this. Okay, so para lang, pag tinatamad ka, so ginaganon mo lang yun. Dinadash mo na lang yung double O na yan, double dot na yan. Okay, so Schrödinger equation. Okay, so we write it as Hamiltonian psi RT. Okay, and then we replace, remember that the energy, okay, remember that yung Hamiltonian operating on psi gives us the energy eigenvalues, energy eigenvalue, okay, times psi of RT, and we replace yung energy na yan with this operator. Okay, so negative or positive IH bar, partial with respect to time, ng psi of RT. Okay, kung saan yung Hamiltonian, okay, dito is given by negative h bar squared over 2m del squared. So, wala dapat yung okay, and del squared plus v. Okay. So, yan yung Hamiltonian. Okay, so now we have yung full Hamiltonian. Okay, full time dependent na Schrödinger equation. So we have the time dependent Schrödinger equation, written as h bar squared over 2m del squared psi of RT plus v of RT, psi of RT equals IH bar partial with respect to time ng psi of RT. Okay, so if we use separation of variables, okay, then we reduce this to the time of variables. We reduce this to the time independent Schrödinger equation. Okay, and yung variable that is the time dependent is given by exponential I omega times t. Okay. Okay. So ganyan yung ganyan basically somewhat, let's say, na-derive quote unquote yung Schrödinger equation. Okay, so what happens to the probability? Okay, remember that yung probability pag nalipat, pag naging time independent na siya. So we have, if we have yung time dependent na solution, okay, yung probability density is given by this, okay, and tawag dito, we can write it as psi of r, okay, exponential, sorry, ganitong gawin ko para clear yung solution. So we can write this as psi of r, okay, exponential negative I omega t, and then ito yung star, di ba? And then psi of r exponential I negative I omega t. Okay, so we have psi star r. And then ang ginagawa ng complex conjugate, okay, dito sa imaginary number is ni-switch niya yung sign from negative to positive. Okay, so magiging exponential I omega t, then psi of r exponential negative I omega t. So this multiplied by this becomes 1. Okay, and then we have psi star of r, psi of r, or it's just psi of r squared. So when you switch, or when you reduce from the time dependent solution to the time independent solution, yung probability density remains the same. Okay. So ganun din para sa normalization. Okay, normalization condition. Okay, for the time independent solution, for the time dependent solution, okay, D3R, we have this equation. Okay, and yung time corresponds, so ito yung time dependent, okay, na normalization condition. Okay, but sabi natin, it's still the same. Okay, kasi ganun pa rin yung makukuha natin after we from deriving yung solution, yung time independent solution. Okay, and then yung normalization condition naman for the time independent Schrödinger equation, okay, can also be given as psi sub n star of x in one dimension na to, no? Psi sub m of x dx is equal to Kronecker delta n m. Okay, so ano yung mga n at saka m na yun? Okay, now sa quantum physics, okay, when you solve the Schrödinger equation, it is oftentimes ang nangyayari, okay, yung eigenvalues is composed of many solutions. So yung general solution, okay, is composed of many solutions. So halimbawa, tawag dito, so let's say for example yung potential well. Okay, if we later on isa-solve naman natin yung potential well using Schrödinger equation, but let me just give you a brief description. So if we have a potential well, okay, yung potential well na yon, okay, it looks something like this. Okay, and if you have a particle inside that well, yung particle na yun will have many states. Okay. But first, yung pinakamababang state is called a ground state, and it looks something like this. So yan yung wave function corresponding to the ground state. Okay, and then meron yung corresponding energy level E naught. Okay, and then meron kang tawag dito, first excited state. So this is the first excited state, okay, with energy E1. And then you have the second excited state, okay, and so on and so forth. So lahat ng nasa taas, ang tawag na dyan ay excited states. Okay? Anong ibig sabihin yan? Ang ibig sabihin yan that if you have an electron trapped in the potential well, it has all of these states. Okay. What do I mean when it has all of these states? Okay. These are all the possible states that an electron can have. So an electron inside the well may be in the ground state. It may be in the first excited state. It may be in the second excited state. Okay. And other excited states. Okay. But you don't know kung aling state siya present until you make a measurement. Okay. So all of these possible states are available to the electron. Okay. And this is called superposition of states. And this is what makes quantum physics, quantum mechanics unique. Okay. Kasi you have a quantum mechanical particle, okay, which can occupy all of these states, or which can have all of these states at the same time. It may be na yung probability na nandun sila sa states ay pare-pareho. Okay? Probability nandun sila sa bawat states na yun ay pare-pareho. It can also be na magkakaiba yung probabilities na yan. But you'll never know kung nasan state siya, okay, until you make a measurement. Okay? And that's what these subscript mean. So this is for n equals 1, n equals 0. This is for n equals 1, n equals 2. So yung subscripts indicate kung anong state siya. Now, if we go back to this equation, okay, this is the normalization condition. Ang sinasabi nito is that for orthonormal states, so psi 1 star of x, psi 2 of x, okay, integral negative infinity to infinity ng dx, this will give us 0. Kasi yung definition ng delta nm is that if n is equal to m, then it is equal to 1. And if n is not equal to m, then it is equal to 0. Okay, but if tawag dito yung integral from negative infinity to infinity, psi 1 star of x, psi 1 of x, yan, n is equal to m, di ba? So equal yung integral na yan sa 1, according to the normalization, according to this definition of the normalization condition. Okay? So yan yung ibig sabihin ng equation na ito. Okay? At ng mga subscripts na nakalagay dyan. Okay? So the subscripts mean na maraming states na pwedeng i-occupy yung quantum mechanical particle. And we describe those states in terms of this, in terms of a subscript n, where n is equal to 0, n equals 1, and 2. Kaya m yung nakalagay dyan kasi they're not necessarily in the same state. Okay, so para lang mathematically compact yung pagsulat nung normalization condition. Okay, so any questions? Okay. Okay, so yeah. Okay, we'll talk more about yung superposition of states later. Okay, but itong concept na to is really, really interesting. Okay, especially ngayon. Okay, because now we hear about quantum computers, quantum computing, and yung superposition states na to, ito yung tawag dito, ito yung tinitake advantage ng mga quantum computers. Okay, and this is what gives quantum computers the edge, because for classical computers, you really force the electron to be in a specific state. But for quantum computers, you allow the electrons to be in all of these states at the same time, do the operation, and then towards the end, saka mo lang alamin yung output, okay, by taking a measurement. Okay, so that makes quantum computer much faster kumpara sa classical computer. Okay. Okay. So let's consider solving this short exercise. Okay, so let's show that if a wave function is normalized, then it remains normalized for all time. Okay. Okay. And this is ano, di ba? This is what should make sense, di ba? If the wave function is normalized, meaning the probability of finding a particle within an infinite overall space, okay, has to be one, okay, regardless of yung time. Okay, if we measure yung probability na makita natin yung particle at time t equals 0, it should be the same at time t equals 10 seconds or at time t equals 10 years or 10 million years and so on and so forth. Okay, kasi overall space yun eh. Hindi pwedeng mawala yung particle within the infinite space. Mathematically, how do we write that? So, ito yung probability, ito yung normalization condition, di ba? In one dimension. Okay. One dimension lang para mas madali yung math. Okay. And how do we say na normalize siya for all time? Ibig sabihin, if we take the derivative with respect to time of this normalization condition, dapat equal yan sa 0. Okay, now, you may be tempted to show a solution which looks something like this. From negative, alam natin na from the normalization condition, okay, we can write this as, di ba, alam natin na equal yan sa 1. Kasi nga, di ba, yung probability na makita mo yung particle ay equal sa 1. And if you take the derivative, okay, of that equation with respect to time, okay, pwede yung sabihin na when you take the derivative of this one, okay, pwede yung sigurong i-argue na when you take the derivative of a constant, then that is equal to 0. Okay, so this is not correct. Okay, this is not the correct way, okay, to show, okay, na tawag dito na yung normalization condition, normalized na wave function remains normalized for all time. Okay, this is extremely trivial and it really has no physical meaning. Kasi itong one na ito, it means something. It means that the particle is found over the whole space. Okay. Okay. And then by taking the derivative, you really want this to operate on this. Okay. And this doesn't make any physical sense. Okay. So dapat ang focus ninyo to prove this premise, okay, is to work on this expression. Okay. Okay. So how do we prove that? So we start with the time independent Schrödinger equation. Okay, anong time time dependent Schrödinger equation. Time dependent Schrödinger equation. So sabi natin H psi is equal to I H bar partial with respect to time ng psi. Okay, so alam natin na yung Hamiltonian, okay, operator is given by negative H bar squared over 2m partial with respect to x, okay, squared plus v of x. Okay. May ko-correct lang ako kasi Para pag na-send sa inyo itong notes na to, tama yung nakalagay. Okay. Okay, so the next is to use this equation. So yan na tayo. So the derivative of the normalization condition dx, okay, can then be written as negative infinity to infinity ng partial derivative with respect to time ng psi of xt squared dx. And naintindihan nyo na kung bakit siya naging partial derivative. Kasi yung psi dito is both a function of position and time. Okay. So where partial with respect to t ng psi of xt squared is equal to partial with respect to t. Okay, alam natin na yung modulus squared niyan is written as psi star psi. And this is then equal to psi star partial respect to t ng psi plus partial respect to t ng psi star and then psi. Okay. Okay. Now we can use Schrödinger equation. So we start from here. Okay, so time-dependent Schrödinger equation. So h psi is equal to IH bar partial respect to t ng psi. Okay. At ang gagawin natin is i-multiply natin to by psi star. So, multiply natin to by psi star. Okay. Ayusin natin konti. Okay, so psi star. Okay, so what do we get? Psi star h psi is equal to ang ginagawa ng complex conjugate sa imaginary number? Okay, ginagawa niyang pinapalitan niya yung sign, right? So magiging negative I, and then h bar, of course, constant yan. Then partial respect to t ng psi star. Oops, sorry. Mali. Psi star, and then partial respect to t ng psi. Wait. Hindi tayo nag-apply ng minultiply lang natin to by psi star. Hindi tayo nag-apply ng complex conjugate on the equation. Okay, so yan ang ginawa natin dyan. Okay, so we have that. Okay, and you can already see one part of the equation here. Okay, so yeah, dyan. So we can rewrite this actually as psi star partial with respect to t ng psi is equal to 1 over IH bar psi star H times psi. Okay. Then, the next step is take the complex conjugate, okay, of this expression. Okay, so ibig ko sabihin, so we have psi star H psi is equal to IH bar psi star partial respect to t ng psi. And kukunin natin yung complex conjugate ng buong equation yan. So, anong mangyayari dyan? So, when we take the complex conjugate, okay, I don't know if you remember from your 122, no? So AB star is equal to B star A star. Okay? And kung tatlo yan, magbabalik-baliktad yung tatlo na yan. So this becomes psi star, H star, and then psi. Okay. Okay, kasi nag-reverse ng order yung psi and psi star. Okay. And of course, yung I magiging negative I, and then H bar. Okay, and then psi star star is psi. And then we have partial with respect t ng psi star, which is not, ito ngayon is this second term. So we have, okay, dagdag na lang ako na. Okay, so we have, for the second term, ano yun? Partial with respect to t ng psi star psi is equal to 1 over IH bar negative, tapos psi star, H star, and then psi. So, itong buong expression na ito ngayon, sa loob ng integral, yung buong expression na yan sa loob ng integral. Okay. So, psi star, partial respect to t ng psi plus partial respect to t ng psi star psi ay equal sa 1 over IH bar. So yung first term, recall, is this one. Okay, and yung second term ay ito. Okay, or ito. Or yan, sorry. So IH bar, psi star, H psi minus psi star, H star psi. Okay. Okay. So, ang tanong na lang is, how are H and H star related? Well, if you recall then from 122, I suppose, equal lang sila sa isa. In general, ang Hamiltonian, okay, is equal to its adjoint. Okay. Ano yung adjoint ulit? So the adjoint is complex conjugate and transpose. Okay, pero since we're not considering Hamiltonian as a matrix now, then we're just taking a look at yung complex conjugate niya. And the Hamiltonian has these properties because the Hamiltonian is Hermitian. Okay, if an observable has this property, then we know that then we call that observable as Hermitian. Okay, and since Hamiltonian is Hermitian, and that means that this will cancel out at equal yan to 0, which means na yung integral from negative infinity to infinity ng psi of xt squared dx, okay, d dt, okay, ay equal ngayon to 0. Okay, so we remember we started out from this. Okay, pinasok natin yung derivative dito, naging partial derivative. And then we expressed this integrand as this. And we ended up showing na yung integrand na yan ay equal to 0. So if the integrand is equal to 0, then of course yung time derivative niya ay equal din sa 0. Okay, and that's that means na yung normalization condition is time independent. So the wave function is normalized for all time. Okay, So at this point, any questions sa derivation? If there's something unclear or dito kailangan yung i-clarify. Okay, wala. Everything's clear, hopefully. Okay. Okay. Now let's start applying Schrödinger equation sa mga physical systems. The simplest physical system, okay, is a wave function. Is an electron that is free. Okay, bago tayo pumunta dyan, meron yata akong hindi na-define. Hindi, okay lang. Later pa pala yan. Okay. So, the simplest system is when an electron is free. Pag sinabing free yung electron, anong ibig sabihin nun? So, the free electron, Schrödinger equation applied to the free electron. Or an electron, oops. Or an electron in free space. So, pag sinabing free space, in other words, yung electron ay walang nararamdaman na kahit anong potential. It is not interacting with its environment. It's not interacting with any other particle. Okay. Kasi if it is, then meron kang potential. Like for example, sa hydrogen atom, the electron is interacting with the nucleus. Okay. So, merong interaction potential yun, which is proportional to 1 over R. Alam niyo yun from electromagnetics, electrostatics. Diba? Kung merong electron-electron interaction, that's another potential. Okay. And so on and so forth. But if the electron is free, or if it is tawag dito, electron is free in free space, okay, then wala siyang ka-interact. Okay. So, yung ibig sabihin nito, yung potential is 0. Okay. So, is 0. Okay, so how do we then use the Schrödinger equation in this case? Baba ko muna ako dito. Okay. Okay, so we start with the time independent Schrödinger equation. Okay. Sorry. Outside of. Okay. Wait. Reading ka. Hamiltonian psi sub n of R is equal to E sub n psi sub n of R. Okay. Kung papansinin niyo, we started from the time independent solution. Okay. Instead of starting from the time dependent Hamiltonian. Okay. Bakit? Kasi yung potential is 0. Right? And sinabi natin na if the potential is time independent, then pwede na tayong, then we can write yung time dependent Schrödinger equation into this time independent Schrödinger equation. We know na yung time dependence ay maibabalik natin by simply multiplying yung solution, okay, with this time dependent function. Okay, so if you write out yung Hamiltonian, then we can write negative h bar squared del squared psi sub n of R plus V of R psi sub n of R is equal to E sub n psi sub n of R. Okay? And yun na nga, yung time-dependent solution is nothing but in time independent solution multiplied by exponential negative I omega. Okay, so obviously this becomes 0, and we are left with this expression. So, nag-1-to-1 kayo, di ba? So that's a second order differential equation, and it's really straightforward to solve. Okay. Ang solution dyan is in the form of an exponential, or you can also use a wave, tawag dito, a sinusoidal solution, okay, or sine or cosine, or both, to generalize. Okay. So yung solution dito, okay, so psi of n r t is equal to, so ito yung time independent na solution plus b exponential negative I k dot r exponential negative I omega sub n t. Okay? So, saan galing yung k na yan? Okay, well, it's easier to understand kung saan galing yung k na yan by writing out yung energy eigenvalues. So, it's given by P, momentum squared divided by 2m naught. Okay. And alam natin na in quantum mechanics, quantum physics, ang momentum is h bar k. So this would be h bar k n squared to m naught, okay, equals sa h bar omega sub n. Okay. So marami sigurong bago sa inyo dito, no? Okay. Well, m naught is the rest mass. Okay. Tawag dito, in 183, makikita nyo na mayroong effective mass, okay, as a result of the interaction ng electron with its environment. Okay. And then, ano pa yung bago dito? So yung itong angular momentum, okay, is, angular velocity ay merong subscript na n, and kaya lumitaw yung subscript dyan kasi yung eigenvalues natin ay meron ding subscript na n kasi yung eigenvalues ay merong iba-iba ring values. So merong eigenvalue corresponding to the ground state, first excited state, and so on and so forth. Okay? So ito yung solution sa wave function, yan yung eigenfunction, at ito yung eigenvalue. Okay? And basically, ganun lang yung ginagawa pag magsasolve kayo ng pag tinitry nyo intindihin yung system. You define the potential, di ba? Tulad na sinabi natin, plug it in dun sa Schrödinger equation, solve the Schrödinger equation to determine the wave function and the eigenvalues. So this is finished. Okay, that's a full, yan na yung full solution. Okay, but how do we make sense of this solution? Okay, so one of the things to do is to tawag dito, is to describe yung particle in terms of this relation. Okay, so itong relation na ito, okay, is called the dispersion relation. Okay, and this is actually, okay, energy. This is a plot of energy as a function of momentum. Okay, paano nangyari yan? So actually, nakasulat dito is frequency, but if you multiply this by h bar omega, then you get energy. And dito nakasulat is wave vector, pero if you multiply the wave vector by h bar, then you get momentum. So this is the plot of energy versus momentum. Okay. And this is one way to sort of understand kung ano nangyayari sa system. Okay, so we have this dispersion relation. Okay, so what this dispersion relation states na yung electron is only constrained to have these specific energies. So it cannot have energies, okay, anywhere else. Okay. Yan lang yung energies na pwede siya. And yung energy na yon is parabolic with respect to the wave vector, to the wave function, to the wave to momentum. Okay, so medyo constrained din yung behavior nung electron na yan. Okay, and as you'll find out later, especially sa 183, sa solid state physics, na as soon as the electron interacts with the environment, okay, yung dispersion relation yan becomes more complicated. But that also allows you to understand better kung ano yung behavior ng system. Kasi you'll understand better yung behavior niya in terms of optically. Ibig ko sabihin, pag nag-apply kayo ng light, you use the dispersion relation to understand kung anong mangyayari sa electron pag nag-apply kayo ng light, okay, with a specific frequency or specific wavelength. Okay? Pag nag-apply kayo ng vibrations, okay, you'll also understand kung anong mangyayari sa system. Okay. Bakit ko sinasabing vibrations? Kasi of course when you apply light, alam niyo naman yun, di ba? From 104, when you apply light, yung electron ay napupunta sa excited state. Okay? And then after some time, bababa siya ulit sa kanyang pinanggalingan, sa ground state. Okay? But there's also this type of tawag dito, sabihin natin perturbation. Okay, you can disturb the system by also applying vibrations. Okay, now itong vibrations na to are also quantized. Okay, so and yung quantization, unit of quantization of vibration is called a phonon. So sa quantum physics, okay, yung light, ang quantum of light is called a photon. And then yung quantum of vibration is called a phonon. And through this dispersion relation, you can understand yung photonic behavior depende sa interaction niya along the y-axis. Depende sa dispersion relation, itsura ng dispersion relation along the y-axis. And yung phononic behavior depende sa nangyayari sa dispersion relation along the x-axis, along the wave vector na axis. Okay? So lahat ito mga preview lang ng ano ninyo, ng 183. Okay. So, questions, clarifications? Okay. Medyo na ano na ba kayo? Na-overwhelmed na ba kayo? How are you all doing? Diba? Okay. Sige. Okay. Yes, salamat sa mga reactions. Buti walang nagre-react na may natutulog. Meron ba ganong reaction yung tulog kayo? Inaantok. Curious tuloy ako. Ako pinatitignan. Okay. Anyway. So, sige. Let's move on. So, okay, so ganitong gawin natin ngayon. Okay, let's say na we want to describe an electron, okay, at a particular position. Okay, in free space. So free space pa rin ito. In other words, wala siyang interaction with anything. Okay. And this time, okay, since napag-aralan na natin na ang electron can be in a superposition of states. So superposition of wave function, each state is described by a wave function. Okay, kita naman natin dito, di ba, sa expression na ito. Okay. So, merong subscript na n, di ba? Subscript na n, subscript na n. Okay, so yung electron na yan can be in a superposition of states. And because of that, meron lang siyang tawag dito, probability na makita siya at a specific position. At yung probability na yun ay tinatawag natin ay nagko-correspond sa kanyang average position or expectation value. Okay. So, we can describe yung expectation value na yun, okay, o yung average position na yun in terms of a Gaussian pulse. Okay? Especially pag photons, di ba? Pag photons, apply ka ng, pag nag-apply ka ng photon sa electron, then yung electron na yun will have, since you're taking a measurement, yung electron na yun will have some average position. Okay, bakit average position? Bakit hindi exact? Remember in quantum physics, you can't really measure exactly yung position niya. So you only measure a range of position, and within that range, meron ka nung average position. Okay, so average position sa gitna ng range, and then yung range na yun ay tinatawag nating standard deviation. Okay. And one of the ways to describe this is through a Gaussian pulse. So ito yung itsura ng Gaussian pulse. Okay, so and mathematically, the way we describe a Gaussian pulse is I of x, and then lalagay ko lang dito t equals 0. Okay, pero explain ko yun mamaya. Equals sa exponential I k naught x exponential minus x naught squared over 4 delta x squared. Okay, so itong term na to, ito actually yung Gaussian pulse. Okay, and then this just describes yung propagation, okay, nung wave function. Okay, and itong amplitude naman na to, okay, has a specific value, which is given by 1 over 2 pi delta x squared, okay, raised to the 1/4. Okay, so yung delta x na yan is the standard deviation. But for a Gaussian pulse, so ang gagawin nyo dito for Gaussian pulse is, so ito ngayon yung kanyang average position, x naught, and then kunin nyo yung maximum value, hanapin nyo yung f value, and then alamin nyo to, saka yung points na yan, okay, yung difference na yan yung delta x. Okay. And it's also called full width at half maximum. Okay. Kasi half maximum and then yung width niya. So it's a full width at half maximum. Yan yung delta x or standard deviation. And in quantum physics, we also interpret that as the uncertainty. Okay. So uncertainty in position. Okay. Ito sinabi ko na yung expression for the propagation. Mayroon yata akong na hindi na-describe kanina, which is this one. Okay. So tawag dito, itong part na to ng wave function, okay, mayroong positive I. At itong part na to ng wave function ay mayroong negative I. Ang sinasabi lang dito, okay, so this is the amplitude. This is this function here is the amplitude, okay, for a wave propagating in the positive r direction. At ito naman okay, is the function okay, for a wave corresponding to it corresponds to a wave propagating in the negative r direction. So if this is your 3D space, so let's say one-dimensional space lang, and you have a wave function that's propagating in this direction, yan yung first term. And if you have a wave function that's propagating in this direction, that's your, that's this expression here. So ito ay propagation. Describes the propagation of the wave function. Okay. And then ito yung Gaussian. Okay. So if this delta x is the uncertainty, then your average position niya is obtained by taking the expectation value of x. Okay, alam na natin yan. Diba? When you take a measurement of an observable, in this case position, you use the expectation value, and then you get the average position. Okay, now bakit t equals 0? So, kinoconsider muna natin yung initial na average position niya and initial na uncertainty in position. Okay? So, ano ngayon ang probability? Ano yung probability density at time t equal to 0? At pala dito. Okay. Sunod pala ako dyan kanina. Anyway. Okay, so ano ngayon ang probability density? Okay, remember ng probability density is given by psi of x t, in this case t is equal to 0 squared, or psi star x equal to 0 times psi x equal to 0. And an effect ng complex conjugate in this case, in this equation, is to change the sign of this. Okay, so we have a star a exponential I negative I a naught x, and then exponential negative x minus x naught squared for delta x squared. Tapos a exponential I k naught x exponential negative x minus x naught squared for delta x squared. Okay. In general, itong amplitude na to can be a complex number. Okay, pero tawag dito, by taking the complex conjugate and multiplying it with its non-complex conjugate, you eliminate yung ano, diba, yung complex component. So this will become just simply a squared. Okay. And ito, multiplied by this will be equal to 1. So we are left with exponential minus x naught squared divided by 2 delta x squared. Okay. 2 kasi minumultiply nyo itong dalawa na ito sa isa't isa. Okay. So that's the probability density, okay, for this wave function at initial time t equals 0. Okay, what about yung momentum? Okay, in momentum, or actually in momentum space, okay, we can write this at, so this is real space. Okay, so in momentum space, we can write this wave function. Okay, at t equal to 0 as 1 over a square root of pi. Okay, exponential negative I, k minus k naught x exponential minus k naught squared delta x squared. Now, huwag kayong mag-alala kung it seems na I'm pulling things out of a hat. So parang magic, diba? But ganun, it is still the same. In momentum space, this is the amplitude. This is just a propagation, okay? Direction of propagation of momentum, okay? Of the wave, sorry. And this is the tawag dito, that's the Gaussian. Okay, well, it doesn't look exactly like the Gaussian, but we'll go to that in a bit. Okay, and yung probability yung density, okay, in momentum space is equal to 1 over a squared pi exponential minus k naught squared to delta x squared over 2 delta x squared. Okay. Okay. Now, tulad ng sinabi ko, it doesn't look like a Gaussian wave function. Actually, a Gaussian wave function should look like something like this. Should look like this over 2 delta k squared. Parang pareho dito, di ba? Yan, pareho dyan. Okay. So ito yung Gaussian wave function. And if we compare these two, ito at saka to, we get delta k is equal to 1 over delta x. Okay. Which means now, sorry, 2 delta x. Which means now, okay, mathematically we have delta k, delta x is equal to 1/2. But if we multiply this by h bar, so if we multiply this by h bar, okay, so we get h bar delta k, of course, is momentum. So delta p, delta x is equal to h bar over 2. Okay, and this is the minimum value for Heisenberg's uncertainty principle. So what this says is the probability or the uncertainty in finding the position is directly related to the uncertainty in the momentum of the particle. So if you want to measure the position exactly, which means delta x is small kasi very certain ka, di ba? Ang requirement is that delta B should be very large. So mataas yung uncertainty sa momentum. On the other hand, if you want to measure how fast a particle is moving, okay, then hindi ka sure kung nasaan yung particle na yan. Okay. And that's because of this uncertainty, Heisenberg's uncertainty principle. Okay. So, yan ang isa sa mga consequences ng quantum physics. In some sense, you can probably relate this sa classical, sa tunay na buhay. Paano? Let's see. Pag halimbawa, may gate. Okay. Merong gate sa subdivision ninyo. Kung nasa subdivision kayo nakatira. Okay. Tapos nagda-drive kayo ng sasakyan. kung mabagal lang yung pag-drive nyo. Okay. Okay, so ang tawag dito, sigurado kayo na lulusot kayo sa gate. Right? Bilisan nyo ng konti. Okay. Medyo hahawak na kayo doon sa manibela. Okay. Kasi hindi kayo sure sa position ninyo, pero sigurado kayo sa bilis nyo. Di ba? And pag bilisan nyo pa ng konti, sigurado kayong ganyan kayo kabilis, mas kakabahan na kayo kasi hindi kayo sigurado talaga na lulusot kayo dun sa gate. Di ba? So the faster you go, the faster you know your momentum. Okay, yung uncertainty in momentum is small. Yung uncertainty na makakalusot kayo sa gate, yung delta x, okay, it will become larger. Okay. So parang ganun siguro yung isang analogous na interpretation, at least in terms of classical physics. Pero sa quantum physics kasi, it's of course it's a different interpretation kasi hindi naman lumulusot sa gate kasi may mga slits ka, okay, in some experiments. But the idea is there, okay, na you cannot measure momentum and position precisely at the same time. Okay, and we were able to derive this from a Gaussian pulse. Okay, na pinatakbo natin, okay, through space. Okay. Okay. Now, just to para lang maintindihan niyo kung saan galing itong mga equations na ito. Okay, I'm going to send you some notes then, additional notes, okay, you can go through. Okay. Yan, para alam niyo kung saan galing yung mga yan. Okay. Hindi na natin i-discuss. Okay. And it's just sort of important to know and understand in the context of deriving yung Heisenberg's uncertainty principle. Okay, so what happens to this uncertainty as time progresses? Okay, kasi di ba t equals 0 pa lang to. Ano mangyayari sa uncertainty nito as time progresses? So, okay. So, ang mangyayari is this. So now we describe a wave function, okay, with a time dependence. Okay, so in momentum space, psi of kt is equal to 1 over a square root of pi, okay, exponential negative I k minus k naught x exponential negative k minus k naught squared delta x squared. And then, di ba, sabi natin, dadagdagan lang natin itong expression na ito. Okay. Para magkaroon siya ng time dependence. Okay. And that's allowed kasi yung potential is zero. Yung electron ay nasa free space. And imbis na n, we write k kasi nasa momentum space tayo. Okay. So nasa momentum space. Okay. Now, sinabi rin natin na in momentum space, okay, yung energy, okay, is given by h bar omega k, okay, or h bar squared k squared over 2 m naught. Okay, and we can expand, we can do a Taylor series expansion of omega here. Okay. Okay. Yung omega na to, gagamitan natin ng Taylor series expansion. And alam niyo naman gumawa ng Taylor series expansion, di ba? Kasi tinuruan kayo ng magaling yung teacher sa 1-to-1 noon kung paano gawin yan, right? Okay. And if you do a Taylor series expansion, so yung first term is f of x naught. Okay, so Taylor series expansion about x naught. Yung second term is first derivative, and yung third term is second derivative. And wala ka ng third derivative kasi yung k mo, k naught dapat ito. Yung k mo is hanggang squared lang. So pag kinuha mo yung third derivative, yung zero na. Okay, so h bar k minus k naught squared over 2m. Okay, at yan yung ipapasok nyo dito. Okay, and kung gusto nyo malaman kung ano nangyayari in real space, do a Fourier transform on psi of k. Okay, and this will lead to psi of xt okay, okay, this will lead to psi of xt equal to 1 over a pi square root of 2 exponential I k naught x minus omega t, okay, omega naught t, integral from negative infinity to infinity, exponential I k minus k naught x minus x naught minus h bar k naught e over m naught. Okay. Exponential negative k minus k naught squared delta x squared 1 plus, lahat ng ito ay exponent, 1 plus I h bar t over 2 m naught delta x squared. Okay, and then dk. Okay. So, okay, medyo maraming nangyayari, right? So, bigyan ko lang kayo ng context kung ano yung mga yan. So, yung first term, this describes yung propagation ng wave. Okay, and this is propagation of each of the individual waves. So this is the phase velocity. This describes, at least yung itong part na to describes yung phase velocity. Okay, which is given by Vp equal to h bar k naught over 2 m naught. Yan yung phase velocity. Okay, and kung mapapansin nyo rito, okay, may equation of motion. Kasi if you recall from kinematics, di ba? V naught xt. Di ba? So yung V naught nyo ngayon dyan, kung titignan nyo is h k naught over m naught. Okay. And that's actually called the group velocity. Okay, and then finally, you have this. Okay, so this is delta x multiplied by a function that is dependent on time. So this expression, so this is the equation of motion for the uncertainty in x. So now we see na your uncertainty actually changes as a function of time. Okay, and it increases kasi di ba plus yung sign eh. So nag-increase yung uncertainty as a function of time. And that's why when we look at this graph, at t equals 0, yung delta x na yan has this value. But, okay, full width half maximum, maximum half is somewhere here. Here, yung delta x increased. Okay, as t, okay, as the wave dito propagates, okay, or as the wave function evolves. Okay, so yan yung nangyayari dyan. Now, again, I'm going to send you all of these notes para makita niyo yung full derivation. Hindi na natin di-discuss yun. So that we can, next lesson, we can move on dun sa dito, dun sa lessons, sa succeeding lessons, application and Schrödinger equation. Okay, but at this point, gusto ko lang i-discuss yung meaning ng phase velocity at saka ng group velocity. How do we picture yung ano na yan, wave velocity tsaka group velocity. So, yan. Okay, so I have this, I prepared this Okay, so here we go. And now I'm going to share to you kung ano ibig sabihin ng ano. Group velocity tsaka phase velocity. Okay? So, ito yung nakikita niyo dyan. And what you see here, first of all, etong nasa taas, this is an individual wave. Okay? These are individual waves. So, magkaibang waves yan. Okay. But when you superimpose, when these waves interact, and remember, bakit may dalawang waves? Kasi nga, di ba, a particle can be in a superposition of states. And each state, okay, I describe by a wave. So this can be one state, and this is another state. And it may mean that yung differences between these two states are very, very small. And if that happens, then you have, then you form a group of waves which has a certain velocity at yun yung tinatawag na group velocity. Pero yung individual na waves na yun ay meron ding velocity which is yung phase velocity. It's described by the phase velocity. And yun yung ipapakita dito sa video na ito. Okay, so these are the individual waves and what you'll see here is the group of waves. Okay. Yan. So makikita niyo na mas mabilis ng konti yung isang yung wave na ito kumpara dito. Okay. And when that happens, then you form these waves. Okay. Okay. Now, at some point, okay, may lilitaw na, okay, forward ko ng konti. Yan. Yan. So, pause natin ng konti, no? So, yung green dot dito, okay, describes yung velocity ng individual na wave. And yung magenta na dot, which yun na doon, describes yung group velocity. And this, ito, ang tawag natin dyan is a packet. That's a wave packet. Yan yung dinidescribe ng group velocity. So kung ipa-play ko ulit yan, ito yung magenta, sinusuntan niya yung wave, yung speed ng wave packet. And itong green, it just follows yung individual na wave. Okay, individual na resulting na wave. Okay, so magkaiba ng bilis yung phase velocity at saka yung group velocity. And this is how we describe yung result or yung wave function. Okay. Okay, so I'm also going to send this link sa inyo. Okay, YouTube link. Okay, para lang mapag-aralan ninyo at maintindihan ninyo or ma-picture ninyo kung paano nag-work yung tawag dito. Yung group velocity tsaka wave, group velocity, phase velocity, and kung paano i-interpret yung equation na diniscuss natin kanina. Okay, so yeah, that's it for today. Meron bang kayong questions? Okay, wala kayong questions. Okay, so kung wala kayong questions, just have a quick announcement. Okay, Wednesday, sabi ko magkakaroon na tayo ng face-to-face meeting. It turns out na hindi pa. Okay, so first na face-to-face meeting natin will be on Friday. So Wednesday, kailangan namin bumaba sa Manila to attend a sort of a workshop or a seminar. Okay, so yun. So ang first face-to-face meeting natin ay sa Friday pa. But para hindi tayo ma-behind sa lessons, okay, magpe-prepare ako ng recorded na lecture. Both for 173 since lahat naman kayo dito except for a few ay nasa 173 ko rin. And for 181. Okay, tapos i-upload ko na lang dun sa ating notes. Okay? But you'll see me in campus starting Monday if you want to do consultations. Okay. So, kung wala na kayong tanong, then I'll see you next week. And yeah. Thank you for coming.